Hello guys, I'm Joseph. Today I'm going to talk about angular motion. I'm going to talk about the homework, about angular motion and also torque. I'm going to talk some physical concept about angular velocity, angular acceleration, then talk about the derivation, then answer for the questions. So let me start from the homework 9.10. So you can see there is the homework description on my screen, and then I'm going to show the steps, and also I will show the calculations. So first one, this question is talking about the acceleration, and there is an electric fan. Then this fan is turned off, and the angular velocity is decreased uniformly. Here, the keyword is uniformly from the 500 to the 200 in just 4 seconds. And we are going to find the angular acceleration in this unit, and also the number of circles made by this acceleration, and in just a 4-second interval. So, to solve these questions, we have to make sure what we know and what we don't know. So in the part A, we know here is the initial acceleration, the initial angular velocity, that's 500, and the final angular velocity, that's 200, and the time, 4 seconds. And we are going to solve the angular acceleration and also the angular displacement. So to do this problems, we have to review the equations. So let's take a couple of seconds to review the formulas what we have on the equation sheet. So if we have a straight motion, then there's an object moving in a distance, and we have 5 parameters to describe this motion, and the initial velocity, and the final velocity, how long does it take, the acceleration, and the displacement. So if we know 3 of the parameters, we can solve the rest 2. So we have 4 equations to solve these parameters. So you can see each formulas contain 4 parameters, and if you know 3 of them, you can solve the rest 1, and if you know 4 of them, then you can solve the 5th parameter. And the same idea in the angular motion. So if you have an object and spinning in an angle, then we have still 5 parameters to describe this angular motion. They are angular velocity, initial angular velocity, final angular velocity, and the time. Then we have the angular acceleration. This is alpha, and we have the theta. So you just need to change the linear velocity by the angular velocity, and we keep the same time. And I replace the acceleration with the angular acceleration, and I replace the displacement with the angle. Then I can rewrite these 4 formulas. That is, so you can see I just changed the velocity by the angular velocity. I changed the displacement by the angle, and I changed the acceleration by the angular acceleration. Then we have similar equations. So if we know 3 parameters, then we can solve the rest 2. So let's go back to the question. So the first question asks us to calculate the angular acceleration. So what we know is the initial angular velocity, final angular velocity, time. So we already know 3 parameters. So we can go to solve the rest 2. That is acceleration and the displacement. So we pick up this formula. That is, the final angular velocity is equivalent to the initial angular velocity plus the change of angular velocity. The change of angular velocity, if this is a uniform deceleration, then we can write in this format. So that's the angular velocity, angular acceleration times the time. Then we are going to do the calculation. But before we do the calculation, we need to convert the unit. The question asks us to use this unit, but what we have is revolution per minute. So we are going to convert the revolution per minute to the revolution per second. So to do this this change, we have the relation that is 1 minute is 60 seconds. So if we know in 1 minute the angular velocity is 500 revolution, then in a second we just need to use this number to divide by the 60 seconds. So this is how we do the convert. You see, the angular velocity could be calculated by the number we have in the description, then divided by the 60 seconds. Then we have the number with the unit of revolution per second. Then we use these two numbers to calculate the angular acceleration. So we use the final angular velocity minus the initial angular velocity over 4 seconds. Then we got a negative number. So the negative means this acceleration has a negative number, and this is a deceleration. And that makes sense because the fan is turned off, so everything slows down. Okay, then the next question is how to solve the angular angle. So here, this is how we do. We use this formula to solve the angle. We have the initial angular velocity, the time, the angular acceleration. So we use the number we just got from the first question. Then we can solve the angular displacement is 23 revolution. So I think in these questions, what we are going to be careful is we have different units. So in case we can use the second, we have to convert the revolution per minute to the revolution per second. So this is the part A. To solve the part B, let's see. The part B asks us to calculate how many more seconds are required for the fan to come to rest if the angular acceleration remains constant. So we use the same angular acceleration, and we are going to calculate how long does it take for the fan to go to the rest. So to go to the rest means the final velocity is 0. So this is the condition hidden in the description. So here, let's make sure what we have in this part. So we have the initial angular velocity, that is 200, and the final angular velocity, that's 0, and the acceleration, this is what we get from the part A. Then we are going to calculate the time. So we pick up the same equation, this one. So we know the angular velocity, and we know the angular acceleration. So to solve the time, that's easy, but we have to keep the units the same. So the 0 is the final angular velocity, then subtract the initial angular velocity and divide by the acceleration. So here we have to keep the acceleration as minus number because this is a deceleration. So if we miss the minus sign, then we will get a minus value for the time. So here, this minus sign is very important. So until now, to make a short summary, that is, after we read the description, we have to make sure what kind of parameter do we have. If we know 3 parameters, then we can solve the other 2. Okay, this is the first question. And let's move on to the next one. The next problem in the homework is 9.1. 26. So this is another problem to help us understand how the angular acceleration means in a specific angular motion. Here, at the t equal to 3 seconds is the time, a point of the ring of 0.2 meter radius rail has a tangential speed. Okay, there's a tangential speed, and we know the number is 50 meters per second. And this wheel slows down. Okay, so we have the negative angular acceleration with a tangential acceleration of the constant magnitude of this guy. So we know the tangential acceleration is this one, and we are going to calculate the wheel's constant angular acceleration. So far, what we know is the radius of the geometry. This is the wheel, and we know the tangential speed. Okay, and we know the tangential acceleration. So we are going to calculate the angular acceleration. So let's review the relation between the angular acceleration and the linear acceleration. So we have this formula. So there is a factor of r between the linear parameter and the angular parameter. So if we have the tangential speed and we have the angular speed, then the ratio is equal to the radius. And the same thing if we have the tangential acceleration and we have angular acceleration, the ratio is also the radius. In this case, we know the radius, that is 2.2 meter, and we know the tangential acceleration, that's -10. So it's easy to calculate the angular acceleration. So here we keep the negative number here because this motion slows down. So we have -10 on the numerator and divided by the radius, 0.2. So we have -50, and here we have to care about the unit of the angular acceleration. That's the radian per second square. Okay. Then, if we are going to calculate the angular velocities at 3 seconds and 0 second, we have to make sure we know the tangential speed at each of the time. So if we know the tangential speed, then we can use the tangential speed divided by the radius. Then we can get the angular speed. So here it is. This is the time. At 3 seconds, we know the speed as 50 meters per second. Okay, so that's easy. We use the linear speed or the tangential speed over the radius. Then we got the angular velocity, 250, and the unit is radian per second. Okay, then let's calculate the angular velocity when time equal to 0, the initial point. So we know this motion has a constant acceleration. Here we have constant angular acceleration. So we can use the formula. The acceleration, the change of the acceleration is equal to the angular acceleration times the time. So the initial here, let me see, is 250, and the 50 is the linear, or also we can say this is acceleration, and this acceleration is obtained from the part A. So in the 3 seconds, we got 400. So here, I just flip the motion. We know this motion is the acceleration, so the alpha should be a negative. But if we go back or we just reserve this motion, we can think about that. The motion is acceleration. If we set the alpha is positive, then we set the 3 seconds is initial velocity. Then the 0 point is the final velocity. So I just reserve this motion. So here I use positive 50. Okay, so the same thing, we use the initial, this is 250, then plus the acceleration and the 3 seconds, they will get 400 radian per second. Okay, this is the part B. And if we go to the part C, the question is, through what angle did the wheel turn from 0 to 3 seconds? So this is a question to calculate the angular displacement. So to calculate the angle, we pick up the relation between the angle, acceleration, time, and velocity. So here, this is what we have. So the angle is equal to the average angular velocity times how long does it take for the slowdown. So in this case, the average angular velocity is defined as half of the initial angular velocity plus the final angular velocity. Then we have the time here. So we just plug in the number. Then we have the average angular velocity is 325 radian per second. So this number is gotten from here. The initial is 400 and the final is 250. So we plus them and over 2, then we get 325 radian per second. And the time is 3 seconds. So we multiply them together, then we'll get this radius. Okay, so we can use the radian, and we know each revolution is 2 pi. So we can use this number divided by 2 pi, then we get the how many circles does it take for this motion. Okay, this is the first 3 questions, and the last one is a little bit tricky. The question is, at what time will the radian acceleration equal to g? So here is another acceleration. To make clear what does this acceleration means, I just sketch a diagram here. For any circular motions, there are 2 kinds of acceleration. One is acceleration in the tangential direction. This is called tangential acceleration. And another one is the radian or radial acceleration, also called centripetal acceleration. So the tangential acceleration only changes the speed, and the centripetal acceleration only changes direction. So in part D, we are going to calculate the time when the radial acceleration equal to g. That means this acceleration equal to g. In these questions, we know the tangential acceleration is a constant. It's always equal to minus 10. So this is a constant. But the radial acceleration is not a constant. It depends on the velocity. So we have the relation between the centripetal acceleration and the linear speed. That is the acceleration equal to the velocity squared over the radius. And it says what time does it take to go to the gravitational acceleration. So we just make these 2 equivalent. So we can go to solve the linear velocity. So we have 9.8 is the gravitational acceleration, and we have the radius 0.2. So we got the linear velocity, that's 1.4. Okay, so the next step is to calculate the time. So the time is easy to get if you know the change of the velocity. If we know the change of velocity, we just divide by the acceleration, then we have the time. So the change of the velocity is the change of the linear velocity. So change of linear velocity over the tangential acceleration. So we got the time. The change of the linear velocity is the 50. This is from here. At the 3 seconds is 50. And then let's go to the the velocity when the radial acceleration equal to g. That's 1.4. Okay, then we divide it by the 10 meter per second square. This is the tangential acceleration. Then we get the time. Okay, so in this case, we have to make sure we can distinguish these two different kind of acceleration. So the same thing, we have two different acceleration. One is pointed to the center of the circle. This is the radial acceleration, and also we call this centripetal acceleration. And this is depend on the linear velocity. The other acceleration in the tangential direction is called tangential acceleration, and this will speed up the motion or slow down the motion. So this guy will change the speed, but this guy only change the direction. Okay, so this is the second problem, and so far we just use the equations to calculate the different parameters like angular acceleration, angular velocity, or the angular displacement. The next thing is that if we know the angular velocity or the angular acceleration, how can we calculate the force? This is very important. All the things should be under the force. Okay, so the next problem is going to talk about a uniform ball and has two small balls and glued to its end, and the bar is 2 meters long and has a mass 4 kilograms. And while the balls each have mass 0.3 kilogram and can be treated as a point mass. Okay, then we're going to find the moment of inertia of this combination about this axis. So here there is a new concept, moment of inertia. This is not familiar for everybody, I think, if you don't take physics class before. So what's the meaning of the moment of inertia? So to talk about this one, I just draw a diagram to help you understand what's this. So if we have a point mass here, I draw a schematic diagram here. This red spot is a point mass, and this point mass is spinning with this axis. This is axis and is spinning about this axis in this way. Okay, and we know in this spinning there is a acceleration in this direction, and the radius goes in this way. Then the acceleration, angular acceleration, goes in this way, and the torque goes up. This is the diagram. And then let's calculate the torque. How much torque do we need to keep this motion? So the definition of the torque is defined by the force on the point mass, then cross the radius, or the displacement from the axis to the point mass. So we have to write these two vectors in this way, and we cannot flip this direction. We can write as the R cross F, because the cross product is not commute. So here, the force, according to the Newton's second law, we know is equal to the mass times the acceleration. Okay, so the next thing is that we don't want to use linear acceleration, because in the angular motion, the linear acceleration is not direct parameters to describe this motion. We are more curious about the angular acceleration, so we changed the acceleration by the angular acceleration. So the angular acceleration cross the radius is a linear acceleration. Then we have a double cross here. The double cross is a little bit complicated to do the calculation, but in the math, we can confirm that the double cross could be written in this way. So this is the formula, and if you are not familiar with this, you can go to check the calculus and the vector analysis. So the double cross could be written in this way. And you can find that the first term is the r dot r, that's r squared. And the second term, you can see the alpha is the angular acceleration that goes up, and the radius is in the plane. So we know the angular acceleration is perpendicular to the radius. So the dot product gives you the 0 result. So this is 0. So the second term is 0. So we only have the first term. That is m, acceleration, and the radius square. And we just flip this order, and we have mr squared times the angular acceleration. Then we define the mass times the radius square as a moment of inertia. So you can think about that. The Newton's second law tells us the force equal to the ma. And in the angular motions, we just use another formula. That is torque equal to the I alpha. So that means the I is inertia. The moment of the inertia is going to replace the mass, and the angular acceleration is going to replace the linear acceleration. Then we don't use force to do the calculation, but we use a torque. So this is a new parameters we are going to describe the angular motion. So if we know the angular motion and we know the moment of inertia, then we can go to calculate the inertia. So this is the calculation for the moment of inertia for the point mass. But if we don't have a point mass, we have a disk or we have any object, how can we do the calculation? So the idea is coming from the calculus. If we have an object, then we can separate the object. We can divide the object by millions of small point mass. So this object is consisted by millions of small mass. I call it dm, the small mass. And we know for each small mass, the torque is equal to the mr squared times the acceleration. So if we want to know the total torque of this object, then I just sum all the torque made by each point mass. So I do the integral. I integrate all the torque, and each torque is equal to the radius squared and the small mass times the angular acceleration. Then the left part, this part, is defined as the moment of inertia. So we know the definition of the moment of inertia. So the next thing is to do the calculation. But the good thing is that we already have the table to tell us how large the inertia is for different objects. So for the regular object, we have the formulas here. This is a table to show how can we get the inertia, the moment of inertia from this table. In this problem, we are going to calculate the moment of inertia for the rod. So the first two are focusing on. So if the axis is in the center of the rod, then the inertia is equal to this formula: 1/12 the mass of the rod times the length of the rod squared. And if we move the axis to the end of the rod, then the inertia increase. Okay, so that makes sense because we find the axis in the center is easier to spinning and then the axis on the edge. So we use these two formulas to do the calculation. So let's go back to the question. So the first question is that if the axis is perpendicular to the bar and to the center. So this is the situation that we are going to calculate the inertia. So the axis is in the center and it's perpendicular to this bar. So if it's in the center, then we pick up this formula: 1/2 the mass of the bar times the distance squared. Okay, And we can't forget there are another two balls. The two balls could be treated as a point mass. So for the point mass, that is the mass multiply the radius square. So there are two balls, so we multiply 2 here. So we sum all the inertia. The left part is the inertia of the rod, and the second part is the inertia of the two balls. Then we plug in the number. We know the mass of the ball, we know the length of the bar, and we know the mass. So let's plug in all the numbers, then we get the inertia. So this is. And the second part is to calculate the inertia when the bar is on the one of the ball. The axis is on the one of the ball. So here, this is axis. The axis, and there is the spinning in this way. Okay, because the left ball is on the axis, so it doesn't contribute to the inertia. So the inertia of the left ball is 0. And this ball will contribute inertia, and this bar will going to also contribute to the inertia. If the axis is on the one end of the bar, we have to pick up this formula 1/3, and this is the inertia of the ball. So we still plug in the number, and we get a new number here, and you can find that the inertia is different from the part A. So that means even if we have the same object, but the spinning axis is different at different place, we will have different moment of inertia. Okay, this is a very important conclusion. So it doesn't guarantee the same object give you the same inertia. Okay, so part C, calculate the moment of inertia when the axis is parallel to the bar and through two balls. So in this case, and if this guy spins in this way, all the mass is on the axis. So the radius here is equal to 0. If the radius is equal to 0, then the inertia is equal to 0. So no doubt. Okay, so this is part C. And the part D, if there is a distance between the bar and the axis, then we can treat each ball as a point mass, and the bar could be treated as also a spinning point mass, because we just sum of them. Then we just use the total mass times the radius square. Okay, the radius is 0.5 meter, so that is the total mass times the 0.5 square. That is. So this is a problem to help us understand what does a moment of inertia means. So this is a parameters using to describe the motion in the circular motion, and we are going to calculate the torque. But before we know the torque, we have to know the geometry, and the inertia is a good parameter to describe the geometry. Okay, so next question, we are going to solve the problem 9.48. And this is a question help us to understand the parallel axis theory. That means we have an object and we know the inertia of the object. But if we just move the axis to somewhere else, and this is a parallel motion, and the inertia will change. But how large does it change? We have the theory here. If the the axis is moving parallel to somewhere else, and the moving distance is d, then the final moment of inertia is equal to the initial moment of the inertia plus the mass of the object times the distance of the axis change square. Okay, so here the description tells us the moment of the inertia of the hoop is mr squared, but if the axis is at an edge, then how can we calculate the inertia? So the inertia here, we use this formula. The inertia, the new inertia is equal to the initial inertia. We already have mr squared, then plus the mass, the total mass of the object, times the d squared. D is the displacement of the moving axis. The displacement of the moving axis is from the center to the edge. So the distance is r. So d is equal to r. So we plug in the r here. So we have 2 times mr squared. Okay, that's easy. So this is a very useful result to show you if you don't know the inertia of the object, but you know one of the special situation, then you can use this formula to calculate the inertia when the axis is not at the center. Okay, so let's move on. The last question, this is the last problem for the homework. So there is a diagram, and we can see there's a cylinder, and this is a pulley, and there's a dropping box. So this problems talking about a dropping box has a speed, and the cylinder and the pulley has a speed, and we are going to calculate the speed. And here we know the mass of the box, we know the mass of the cylinder, the radius of the cylinder, and we know the mass of the pulley and the radius of pulley. So we know all the geometries in this system. And another important information is here. We are going to calculate the speed when the box has fallen 2.5 meters. So if there are many body systems, we don't want to use Newton's theory to calculate the speed. What we want to do is use the energy or the work theory to calculate the speed. Because if we know the kinetic energy, then we can going to obtain the speed. So here we are going to use the work energy theorem, and in this case, the only work in this situation is gravity. That the gravity has done the positive work and make this system moving. So the work done by the gravity should equal to the increase of kinetic energy. So we write down the formula here. The left part is the work done by the gravity. So the mass of the box times the gravitational acceleration and the displacement. This is 2.5 meters, and this is the work from the gravity. This is equal to the kinetic energy. In this system, we have 3 guys in the motion, so we have to sum the kinetic energy for each one. So we have the kinetic energy for the box, we have the kinetic energy for the cylinder, and we have kinetic energy for the pulley. For the box, since the box moving down, so the kinetic energy is easy. This is mass times the speed square. But for the cylinder and the pulley, this is not a linear motion. They are doing circular motion. So for the circular motion, the definition of the kinetic energy is defined in this way. This is equal to the 1/2 times the inertia, the moment of inertia, and times the angular velocity square. So if you just compare these 2 parts, they have the same 1/2 factor, but the mass is going to be the inertia, and the linear velocity is going to be the angular velocity. So this is very easy to remember. So in the circular motion, this is the inertia times angular velocity square, but in the linear motion, this is the mass times velocity square. So we sum these three. This is the total kinetic energy. This is equal to the work done by the gravity. And we know for the cylinder, if we go to look for the table of the inertia, we know the inertia of the cylinder is 1/2 the mass of the cylinder times the radius of the cylinder. And also, we have another condition, that is the angular velocity is equal to linear velocity over the radius. So we can plug in these two terms to replace the inertia and the angular velocity to make sure we only have one unknown parameter. So here, this is what we have. And we plug in the inertia, and also we plug in the angular velocity by using the linear velocity over the radius. Okay, and we assume all the velocity on the string is the same. If there's no slip, then this assumption is good. So here we have the kinetic energy of the box, kinetic energy of the pulley, and the kinetic energy of the cylinder. And we have the work done by the gravity. So we do the simplification, then you can see the radius of the pulley just gone, and the radius of the cylinder is gone. So at the end, we have the mass of the box, the mass of pulley, the mass of the cylinder. And you can find that the kinetic energy is independent on the radius. Okay, then we can go to solve the linear velocity of the box. And for this equation, there's only one unknown, that's the velocity. So the velocity is solved in this way. So we plug in all the number, then we have the linear velocity in the meter per second. So let me just give a short summary. If we have many body system in the motion, and we are going to calculate the speed, the first equation in our head should be the work energy theory. We don't want to use the Newton's theory to solve the many body system. So in this case, if we know the work, then we can know the kinetic energy. The kinetic energy will give us the speed. So that's all. So we talk about 5 problems for the homework, and if you have any questions, you can email me. So here, thank you for watching, and my email is here, and we will see you next time. Thank you.